Okay, good afternoon. Today we'll be studying accuracy of the parameters and radar waveform analysis. You can take notes and then ask your questions at the end of the lesson, as there might be some gaps when you have questions, when you speak to the microphone. So just take notes and then ask your questions at the end of the lesson. Okay, here is the outline. We'll be first looking into the accuracy of parameter measurements, namely range, Doppler shift, so speed and angle. And then we'll be studying ambiguity function, which is very critical for the waveform design in a radar system. And then the pulse compression, one of the most important method or technique that we use in radar systems, pulse compression. Okay, let's go back to the very beginning and then remember the waveform that we transmit. We got pulses modulating a sinusoid. Okay, and sorry, we have pulse duration or pulse width, which is tau, and pulse repetition interval, let's say TP here. Okay, and we got an amplitude A or power, peak power, whatever we use. So this is the signal that we transmit, and then we get an echo signal from the target. Sorry again. It might be, let's say, something like this. So this is an echo coming due to the first pulse, let's say. It has an amplitude again, an envelope, sorry. And of course, we expect some noise and then a distortion on this pulse. So even if we transmit a rectangular pulse, the received echo, the envelope of received echo or signal will be distorted, noisy envelope, and the time duration from this the trailing edge of the transmitted pulse to the leading edge of the next pulse will give us the time elapsed due to the signal traveling from the radar to the target and then return back to the radar. So this gives us the range information. And it's quite important to then measure this TR. And since we have distortion due to the noise, even either in the channel or in the receiver of the radar system, we expect some error. Now, in this slide, we simply give a model for this error, how much error we can expect in time duration, TR. And then we have error in range. So mathematically then, if we have an RMS error on range R, it's going to be RMS error in this time duration, right? By the way, let us go back to RMS error, how to measure RMS error. For RMS error, it's a root mean square value actually. So we assume that we have a collection of data. Let's say R cap, which is measured range, minus the true range, divided by the number of samples, let's say n. So if we get this average, let's say from 1 to n, and its square root will give us RMS, root mean squared value of the error. Okay, so this then corresponds to error. Sorry, there's a square root here. This is error, and there should be a square. So R cap minus R to the power 2. So this gives us average, so mean square value of the error. So here delta R corresponds to this RMS distance error. And this is proportional to the error in time. Why? Because of the error due to the noise. Now, on the right-hand side, we got two pulses. These are not purely rectangle, smoothed pulses, which is quite realistic because in practice we do not have a perfect rectangular pulse. There's always a rising edge, okay, rising and leading edge. And if we do not have any noise, then we expect that we got a smooth pulse, as shown here, a solid curve. Okay, when we got noise, then this solid curve becomes one whose values are randomly varying due to the random noise, and the dashed curve represents noisy signal, noisy pulse. Now, let's see then the slope of these pulses, the pulse without noise and with noise. For the clear pulse without noise, we got the rise time, PR, and there is an amplitude, A. So if we write the slope of this curve, this line actually, okay, from here to here, that's going to be a triangle, and simply that's going to be A over TR. Okay, we expect that on average, the slope of this curve, this line actually, and this line should be equal. So then we can write the slope of this line and then this line, and then equate them in order to estimate the error, RMS error. Okay, so how can we write the slope for this curve? We again take the amplitude, which is n of t, okay, here. Sorry. Okay, we take the, again, amplitude and then the time difference, which is delta TR, it's error. So it's going to be n over n of t divided by delta TR. So we simply have two triangles. Okay, one is delta TR, n of t. The other one is tau r, sorry, TR, A. So they have the same slope. Then we equate them and we can write this equation. Okay, here delta TR is unknown. This is the measured error. Now, suppose that we have many such values. Okay, so we get the RMS delta TR simply as square root of sum over, let's say, 1 to n samples, and then delta TR estimated minus delta TR measured square over n. Okay? So this can be written, this can be written as delta TR squared, its average, so this is averaging operation, and then its square root. Okay, 1 over 2. So this corresponds to this value actually, RMS TR, RMS value of the error, time error. Now, then I can write similarly here the noise. Noise is also a random process. So n squared average squared 1 over 2 is simply again summation n cap of t minus n of t squared divided by n from 1 to n. Okay? So then we can write RMS error in terms of the amplitude of the pulse along with the RMS of the average of noise. Okay, we can write signal power and amplitude relation by using a cosinusoid. Let's take, for example, x of t, a of t, cosine 2 pi fct, and then get its power. It's going to be x of t magnitude squared dt from 0 to the period 0 to t, and then get the power. It's going to be a squared over 2. Okay, and if we say if we equate this to power, then the a squared is going to be 2s, 2 times the power. So we can then simply convert this into a power form, and the noise power for a random process, noise power is simply expectation of n of t squared, okay, from probability theory, we know it, which is actually variance of n of t. Okay, so we can then use this and then write the RMS error in terms of signal to noise ratio, which is a quite important parameter in radar systems. Then RMS is dependent on the rise time and signal to noise ratio. If we increase signal to noise ratio, the RMS error decreases. If we increase the rise time, RMS error increases. Okay. Next, I can rewrite this equation by using let me clear this part. I can rewrite this equation in terms of energy. Energy, how? Energy is equal to the power times the pulse duration, so S times tau. And the noise power can also be written as the noise power spectral density times the bandwidth. And the rise time will be the inverse of the bandwidth. How? We now look at the receiver, the radar receiver, how to measure this TR. From the antenna, simply we got an LNA at the radar receiver, we know it, and then a mixer, okay? And then we got an IF stage, which is a filter with an amplifier, we say. The received signal has a frequency, let's say FRF. After down conversion, here we got let's say IF. Okay, so we got simply a pulse with an envelope, just like this. But due to the filtering here, okay, due to the filtering here, it is just a perturbed version of this, okay, just like this. For example, smoothed version. So this is due to the fact that there is no filter which can allow all the components of a rectangular pulse. Whenever we apply a rectangular pulse to a filter, to a system, any system, we always get a smoothed version because the spectrum, the frequency content of a rectangular pulse, pure rectangular pulse, extends from minus infinity to plus infinity, which means that we got an infinite bandwidth signal. Since we do not have an infinite bandwidth filter, then we always have some kind of distortion or smoothing on the pulse. And this IF then, the bandwidth of this IF filter here will be determined by the rise time, actually. Inverse of the rise time will give us the bandwidth of this filter. So here then B is the rise time. I mean, it's inversely proportional to rise time, and it's related to the bandwidth of the filter. Then we can write RMS error in terms of the bandwidth of the filter, the pulse duration, as well as the energy and noise power spectral density of the noise. Okay, so this is RMS error for the leading edge. We just derive it for this leading edge. We can use this, we can apply this to the trailing edge as well. So together, then that's going to be an averaging operation. Let's say this is the leading edge, and we got a trailing edge here, and then get its average, and its square root will give us a factor of 1/√2. So we simply reduce RMS error by using the errors we measure for the leading edge as well as the trailing edge. Okay, now instead of using the previous equation, now we define a parameter beta, which is effective bandwidth, and it's related to the I'm sorry. It's related to, it's dependent on the bandwidth of the IF filter, the duration of the pulse, as well as the pulse width at the IF. So note that we got two pulses here, two different pulses here. One is entering into the IF stage, which is perfectly rectangular, 1 at the output of the IF. So we simply use a filter here whose effective bandwidth is dependent on the parameters that we choose here. For a rectangular pulse, let's take, where the BS, which is the spectral bandwidth of the IF stage, times the tau r, which is the pulse width at IF stage, is much greater than 1. So this is perfectly rectangular. Usually it's not possible, of course, to get this, but beta can be written in this form. And then RMS error becomes like that. Okay? So if we got a rectangular pulse with this condition, with this parameters, then we can determine RMS error approximately using this equation. If we consider a quasi-rectangular pulse, where B tau r is equal to 1, which means that the bandwidth is half of the spectral bandwidth at IF, then beta is going to be 2.1 B, and the RMS error becomes like this, okay? Simpler than the previous one. Now, again, remember this, we got an IF stage here. We got an input pulse, okay? And we got an output pulse whose envelope, you see, is different from the envelope of the input pulse, okay? So this is about designing of this IF stage, or designing a pulse shape, actually. So somehow this is pulse shaping. For this, let us remember a rectangular pulse, simple rectangular pulse whose duration is tau, and its Fourier transformation is going to be sinc f tau, okay? So if we show it in here, let's say it goes to infinity like this. Okay, this is the Fourier transformation of rectangular pulse. So sinc f tau, let's say. Now, at IF stage, we somehow make this rectangular pulse band limited. We cut out these side lobes, okay, and take this part only, which is BS, okay? And if we consider the positive side only, then its bandwidth is going to be BS over 2, okay? So this is what we do here. So this signal, this rectangular pulse, becomes quasi-rectangular pulse, and it's illustrated right here. As you see, there are two filter outputs here. For the solid curve, solid pulse, the video bandwidth, so the IF bandwidth, is BS over 2, which is 1 over tau r. For dashed one, the filter output is tau over, 6 over tau r, which is 6 times greater than this one, which means that its side lobes will be suppressed well for this dashed curve, okay? So now then we can think about which waveforms will be more appropriate for reducing RMS error in range. Here is a list. Gaussian pulse, cosine pulse, triangular pulse, each has a time waveform shown in here, and the effective bandwidth right here. Remember that RMS error was proportional to 1 over beta. Okay, so we'd like to make this beta as high as possible in order to reduce RMS error. Now, actually, there is no big difference between the waveforms. Each might have a different advantage. In the literature, cosine type pulse seems to be quite appropriate according to the discussions in the textbook. So it was about range error. How about the Doppler shift? So speed error. Remember that the speed of the target can be given in terms of the Doppler shift and wavelength. Now, wavelength is constant, then if there is an error in the speed, it's going to be about the error of the Doppler shift. Okay, so we use the same development, the same methodology in range error derivation. Instead of time, now we got frequency, so Doppler shift. So RMS error on frequency. Okay, and it's given in the same form, except that instead of beta here we got alpha. Alpha is the effective time duration. In the range we use effective we use effective bandwidth beta. Now we got effective time duration, and it's given with this formula. Again, the signal, as you see, that we use is important. And we have two cases again, rectangular pulse and quasi-rectangular pulse. For each of this, we got a different alpha value, as you see here. And then for each of this, then we got a different RMS error on frequency. Here's an exercise. Please do it at home, and then let's discuss your questions if you have any. Here, be careful on the speed. It's given not, and also EB over N not, which is given dB. Okay, and you have to convert this into ratio, just taking 10 to the power 2.3, for example. Otherwise, the numbers may not be reasonable. Okay, I'm sure that you can easily solve this. There is nothing difficult here. Okay, how about the angle? We are going on the same methodology. Instead of previously TR and F, we use theta, which is the angle. Okay, again, remember that with a radar, we measure range, we measure speed, and angle. Okay, so this goes to about TR, this goes to Doppler shift, and this goes to the angle, simply theta. It's about the antenna model, of course, for the angle. We'd like to make small beam width in cross range, either elevation, let's say theta or phi. Okay, phi. So azimuth and elevation. Then this is about how we illuminate the antenna, and we define then gamma, which is effective aperture width of the antenna, and it's related to the illumination, the current that we apply to the antenna. And there are several different distributions of currents. Here, A of C is current distribution or illumination. In other words, And for cosine type illumination, gamma becomes 1.13 d over lambda. Here d is the size of the antenna, lambda is the wavelength, as you know. For triangular illumination, it is smaller, and then for parabolic illumination, it has a minimum. And for each of this, we can determine the error in angle, and we can determine beam width accordingly for each of this illumination. So, as a conclusion, we can use the model the error in the range and in speed and angle by using the same methodology and the parameters alpha, beta, and gamma. Okay. There is one more exercise here, very similar to the previous one. Be careful about, again, the units here, degree and milliradian. This should be converted appropriately in order to get the correct result. Okay, it was about the discussion on accuracy of the parameters in a radar system. Next, we'll be discussing ambiguity diagram or ambiguity function. Okay, let's go back to the match filter that we have discussed 2 weeks ago. It was about the receiver structure that we used in radar systems. And again, consider the radar system with a target here. And we transmit an S of t, which is a pulse sequence typically. And then we got an echo signal, which let's say as receive it of t. So the perturbation due to the channel here, the medium here, and interaction with the target, we got receive it echo, which is which could be quite different from what we transmitted. And the goal of the match filter here is to maximize the SNR here. And it's defined with respect to the transmitted signal. So H of t is simply proportional to S of t. Somehow we derive H of t from S of t, and we know S of t, then we know H of t. So it's quite easy to design a match filter once we know what we want to transmit. Okay, and impulse response of match filter, as we have derived previously, is the complex conjugate of the spectrum of the transmitted signal times exponential function, which includes a TR prime, which is the estimated range, which is the estimated time due to the fact that pulse travels to the target and return to the radar. Okay, an impulse response then can be written as complex conjugation of the transmitted signal. It's just shifted by TR prime again. Note that S of t is a complex signal. Okay, in our previous analysis, we always take a rectangle just like this, right? A cosine 2 pi f 0 t, just a summation of this. So many cosines, okay, with duration tau. So we just write here, let's say k times t. T is the PRI. TP is the PRI. So we can write a summation of rectangle times cosine when this is a real signal. But actually, in most of radar systems, S of t is complex signal. not a real signal. Okay, so we talk about complex conjugating here. Okay, what is the output of the match filter? This is, from the systems signals and systems course. If we get an x of t, the output y of t is going to be x of t convolution h of t. So this is just like this convolution of received signal with the h t minus tau, right? Which is convolution with integration. Here, TR prime is the estimated round trip delay, as we said earlier. Now we use this and try to derive ambiguity function. For this purpose, let's define an S of t first, a generic S of t, which is u of t times exponential j2 pi f 0t. Here, u of t is a complex function, complex modulating function, and its magnitude is going to be the envelope of the radar signal at f0. Okay, so S of t magnitude is going to be u of t magnitude. So we got it, and then transmit this S of t, and then get the received signal, which is going to be the shifted version of the transmitted signal by t0, which is true time delay. Okay, so this shows the delay, time delay, true time delay to the target. Okay, and TR prime is estimation. Okay, not the difference. TR prime is the estimated round trip delay. T0 is the true round trip delay. Okay, so there's a difference between them, and we'd like to determine that this difference actually. Try to estimate how much it varies, so that we can estimate the capability of the radar. So we insert this as R and S here. So we see that the signal, sorry, not S prime, SR of T and S complex conjugate T prime, T minus TR prime. And then we see that we got two exponentials as well as two U functions. Each is delayed by different times, T0 and TR prime. For simplicity, we can set the center frequency F0 to 0, and then T0 to 0, so true time delay, and TR prime as minus TR. Okay? Then this equation, this integration becomes like this. Okay? Which is called ambiguity function. Okay? Ambiguity function. So, you see, ambiguity function has two parameters. One is TR, which is the estimated round trip delay. And the other one is FD, Doppler shift. Okay? So here then we consider a target which is in motion, moving. Okay? And we'd like to determine its range and speed. Range will be extracted from this TR, and speed will be extracted from this FD. If the target is stationary, then we expect that the Doppler shift becomes 0, and then the ambiguity function will be simpler. As we again remember from Doppler space, if the Doppler shift is positive, it means that the target is approaching. If it is negative, it's receding, it's going away. Okay? So what properties does the ambiguity function have? There are 5 here. First of all, the the maximum value occurs when the TR and FT become zero. Okay, it's simply the energy simply related to the energy of the ambiguity function. There is a symmetry over x and y axis. Okay, x and I'm sorry, not x, range and Doppler axis, let's say. So here it's illustrated. This is the range, so time, and Doppler axis. So let's say speed and range. Okay, because Doppler shift corresponds to speed of the target. TR, the round trip delay, is simply corresponds to range. So on both of these axes, it's symmetrical. Okay, this equation 2 says it's symmetrical. On the TR axis, so range axis, it's the square of the signal u of t times conjugate u of t, and over the ft axis, it's just like inverse Fourier transformation, square of inverse Fourier transformation of u squared. Okay, so you see the heart of this function is actually the transmitted modulating signal, right? Modulating signal. Once we design this signal, we simply obtain an ambiguity function accordingly. Volume under the surface of the ambiguity function is going to be similar to the equation 1. It's proportional to the energy squared. Okay. Theoretically, ambiguity function, as we can understand from the name, that's about uncertainty. Somehow, it's a metric, it's a function showing how much uncertainty do we have on range and speed axis. Okay, so in order to get unambiguous range and speed, we expect that the ambiguity function becomes a direct delta. Okay, which means that there is no ambiguity over the speed and no ambiguity over the range. This is theoretical, of course. There is nothing like this. One approximation to this theoretical one could be something like this, just similar to a cone or something like this, where we got a single peak. It's spread equally over the Doppler axis and range axis, and the width of this cone-like shape is proportional to the duration of the pulse and the bandwidth, okay, of the pulse. In reality, this is not like that. Here is what we can see for rectangular modulating signal when the pulse duration is large and then small. As we have shown in previous slide, the width of the ambiguity function is proportional to the pulse width and pulse width over the range, and the inverse of the pulse width over the speed. Okay, again, this is speed and this is range axis, so time and frequency Doppler shift. When we take a large tau, then the width of the ambiguity function, as you see, is larger over the time axis compared with the with that on the speed axis. Okay, it's narrower in speed axis because the bandwidth in simple rectangular modulating signal, the bandwidth is 1 over tau. Okay, so if I increase tau, bandwidth decreases. and then the width of the ambiguity function increases over range and decreases over speed, which means that the speed can be measured more accurately compared with the range, because uh, wider the ambiguity function in an axis, uh, uh, lower accuracy in that axis. When we get a small tau, short pulse, then we see in this case the ambiguity over the uh, uh, ambiguity over the Doppler axis will be greater, and ambiguity over the time axis will be smaller, uh, which means that we can measure the range more accurately. Okay, so what we can, or what information we can derive from ambiguity function? Here is, we see a list of the capabilities of a radar regarding with the ambiguity diagram, ambiguity function. We can have an idea about the target detection, how accurately we detect the target. It's about the signal's energy content. So it was about E, simply 2E. Higher the energy, higher the target detection capability. We can have an idea about the measurement accuracy, which is about the main response at the origin. The width of the ambiguity function over the range and speed axis will determine the accuracy of the radar in range and speed. Resolution is also related to the main response, central response. Normally, there may be many different peaks, many peaks over the range and speed axis for an ambiguity function. But we take the main response at the center to have an idea about the resolution. Narrower the central response, higher resolution in range and speed. It's about ambiguities as usual. High responses in magnitude to the peak at the origin means that more ambiguity, and we do not determine the range and speed, consequently, of the target. It's also about the clutter rejection. If we know the clutter speed or range, then we can align or we can design the waveform actually in order to avoid clutters. So we simply synthesize a waveform for a predefined ambiguity function. So we can start with an ambiguity function and then synthesize our waveform. Okay, I just want to have a break here. Okay. So the last topic of the lesson, pulse compression. In previous slides, we compared short and large pulse widths, ambiguity for short and large pulse width. One way to reduce that ambiguity is to use pulse compression. We simply divide the pulse into subpulses. very short pulses, and transmit the signal. In this way, we reduce the peak power, but increase the bandwidth. And since the sub pulses will provide a higher accuracy in range, so higher resolution in range, and the long pulse will increase the resolution in speed, we achieve better accuracy in both speed and range domain. Okay, let's see an example for a surveillance radar. Pulse duration is pulse width is 1 microsecond. The peak power is 1 megawatt. Then the energy per pulse will be 1 joule, and we got a resolution of 150 meters. If we have a range resolution of a desired range resolution of 15 centimeters, then we can generate, we have to generate 1 nanosecond pulses, and for 1 joule per pulse, we need 1 gigawatt, which is impossible. So in order to achieve such a resolution for that energy, with this energy, there is no way to do this by using standard or simple pulse radar system. Instead, then we can use pulse compression. It provides range resolution, accuracy, glint reduction, multipath resolution, clutter reduction. You see, there are too many advantages of pulse compression. The cost will be the complexity, of course. You need more complex signal processing, more complex system design. Here's an illustration showing how we implement pulse compression. We got a long pulse, as you see, a typical pulse, let's say on the order of milliseconds, and we divide this pulse into sub-pulses, okay, whose duration is much smaller than the large pulse. Sometimes one out of let's say we transmit 1,000 pulses, sub pulses to a long pulse of T, let's say. There are two basically ways to implement pulse compression. One is to use frequency modulation. The other one is phase modulation. Amplitude modulation is not popular, is not applicable in most of the radar systems. We mainly use FMOP or PMOP, so frequency modulation on pulse and phase modulation on pulse. This means that we either change the frequency from sub-pulse to sub-pulse, or we change the phase from sub-pulse to sub-pulse, okay? Most of the LPI, low probability of intercept radars, are based on the use of pulse compression. They are quite difficult to be detected by electronic intelligence or electronic support measure systems because they use very low power and they simply spread the power over a very huge band on the order of gigahertz sometimes. If you do not know how FMOP or PMOP implemented, you couldn't detect the signal. You couldn't detect the radar. There is a very critical parameter that we come across in pulse compression radar. compression ratio, which is the duration of the long pulse divided by the duration of subpulses. It's also called BT product, and here the bandwidth B is defined as 1 over tau, the small pulse, subpulse, for phase modulation on pulse, and F2 minus F1 for FMOP, frequency modulation on pulse. So there are two different definitions for bandwidth. You have to be careful on the bandwidth of pulse compression radar. Here is several illustrations regarding with the FMOP, frequency modulation on pulse. Actually, you have already studied this as FMCW radar. That's a chirp signal, simply up chirp or down chirp. Here is up chirp, here is down chirp. The frequency of the pulse, let's take, this is the long pulse we are talking about, and the frequency starts from F2 and then decays linearly down to F1. So the frequency of the pulse in the start point is quite much above the frequency at the end of the pulse. In up chirp, it's opposite in down chirp, and as in most radar systems, we use match filter detection. We can use match filter detection in FMCW or FMOP systems, and the match filter is mathematically an autocorrelation process. So we simply correlate the received signal with the with itself actually. Remember again the impulse response of match filter. It was X complex conjugate T minus TR, right? So if I convolve the received signal with H of T, that's going to be convolution, which will be autocorrelation when I choose this TR appropriately. So it's just like autocorrelation. And the output of this process, this filter, sometimes it's called compression filter, it corresponds to match filter, is quite important. We'd like to, in time domain, we would like to get a pick, single pick, no side lobe. So theoretically, we'd like to get something like this. Okay, this is the ideal one. But in practice, it's not possible. We got side lobes. That's one of the biggest problem in detection. So here is FMCW radar. We have already studied this in laboratory, as you might remember. We use VCO as a generator, and then we use a power amplifier here, and then we got an antenna directly connected to an antenna. We do not have TR model in the laboratory. For the receiver, we got a second antenna, which is connected to an LNA, yeah, and then mixer with this VCO. Okay, so instead of local oscillator, we got VCO. So mix them up and get IF. Okay, and we simply use a low pass filter here and connect a spectrum analyzer to see the bit frequency, which gives us the range. Okay, we did not use a pulse compression filter, detector, and video amplifier in the laboratory. It's going to be the second stage, where we'll use a digitizer here and use FFT or match filter to get the range and speed information. Okay, let's go back to the ambiguity function again for rectangular pulse for low and high PRF cases. For low PRF cases, you see this is the speed axis, this is the time range axis, and we have ambiguities on the speed axis. We do not have ambiguity on time axis, so we can then accurately measure the range, but we will have ambiguity in speed measurement. On the other end, for high PRF, we have ambiguities over the range axis, while no ambiguity over the speed axis, right? This was a very common discussion, common problem that we have talked about in MTI and pulse Doppler radar. One was good at speed measurements, the other one is good in range measurement. So there is a problem here, as you see. There should be a trade-off between speed and range. And the solution will be FMCW radar, where linear FMCW radar, where we have somehow improvement on both range and Doppler's axis. Here's the Doppler axis, here's the range axis. For any pulse radar, we got an ambiguity function like this or like this. Now you see for FMCW radar, that's slanted, but 45 degrees. And then when I look at the amount of ambiguity here, it's relatively smaller than this should be greater than this one actually, smaller than the standard rectangular pulse radar. It's again smaller in the speed measurement. So we simply reduce both speed and range ambiguity by using FMCW radar. How about phase modulation on pulse? Instead of transmitting varying frequency in phase modulation on pulse, we again transmit a sinusoid at a constant frequency but varying phase. So we can simply illustrate that just like a sinusoid here, and then change the phase. Okay, so change the phase again. Or we can, for example, here, we can start just like this. Okay, there's going to be discontinuities sometimes. These are different. These are cosines or sines with different phases, initial phases. So you see there are transition from one phase to another, here, here, and here. So you can imagine that I just use a binary sequence, let's say 1, 0, 1, 1, 0, 1. So if I know this sequence, if I know when the signal changes its phase, then I can decode this signal. Otherwise, this signal is going to be just noise for me. Okay, so that's the idea in phase modulation on pulse. Here, for example, we have a binary phase modulation on pulse, let's say. So there are two phases here, plus and minus, let's say cosine and sine, for example. Same frequency, I just transmit cosine, let's say binary 1, and sine for binary two. So plus and minus simply. So cosine, 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 sine, sine, cosine, cosine, sine, cosine, sine, cosine. So I got 13 bits simply to construct a pulse of duration t. Okay, so then I have to know this code, and this is one known as Barker code, which has which is known with its low side lobe levels. Okay, here, for example, we have code elements 2, 3, 4, and until 13. 13, the side lobe level is minus 22 dB. That's the match filter output. Let's say this is match filter, and here we have FM, PMOP signal, and the output here S prime of t. Remember that for a rectangular pulse, for example, if we got a rectangular pulse, the output was a triangle. If this is tau, then the duration is going to be tau, tau, so 2 tau. So we expect something, a peak at the output to detect the signal when there is a noise. Because when there is a noise, this is going to be just a noisy version, just like this. And if I have side lobes, strong peaks in here, then it's likely that I can make an incorrect decision regarding with the echo signal, whether there's a target or not. Okay, so this autocorrelation function is quite critical. We'd like to suppress the side lobes down and try to get a very high peak here, and try to increase signal to noise ratio in this way, which is the goal of the match filter. And this is, as you see, simply related to the signal that we transmit. If we choose an appropriate signal, yeah, just like the sequence, then I can suppress those side lobes and increase the signal to noise ratio, so increase the probability of detection. Okay, one another example of compression radar is frequency coding radar. So in previous slide, we have described frequency modulation, continuous wave radar, LFM, or linear frequency modulation radar. Now in here, we got stepped type radar. We got, let's say here, 24 pulses to construct a single long pulse. And for each of the sub-pulse here have a different frequency. So there is a code, frequency code for one long pulse. There are several such codes called Costas codes. And the order of the frequencies are simply changed. And it's very similar in one sense. It's very similar to the phase modulation on pulse. Okay, this is sometimes called frequency hopping code because at every new pulse, sub-pulse, the frequencies change randomly, which makes the system robust to noise and then jamming. Okay, it's quite difficult, of course, complex system. Here's the last slide of the lesson and also this semester. there is a list here. You see the advantage of FM, so fmob and pmob. Time side lobes, for example, one property, Doppler, for phase modulation on pass. There needs to be a filter bank and ambiguity function reached, but thumb tag, sorry, in pmob. A pass compression filter, the properties of a pass compression filter, complexity. You see, fmob is more complex than pmob is more complex than fmob. An application, so for high resolution applications, just like try to imaging something, then the fmob might be better. If we need long passes to transmit, then we use pmob. There are some others listed here. So you can take a look at the textbook where there is a discussion on fmob and pmob. Okay, that's the end of the lesson, end of the semester. Thank you for listening and for taking this course. We can take your questions now, and then we can arrange a discussion hour, an office hour, regarding with the solutions that you have done.